Okay, so welcome to the lecture guys, and in this lecture I'll be talking about an optimizer. So optimizer is a major component in any neural network. Without that obviously you can't build it. And why we are going to use an optimizer, what kind of a optimizer that exists, and what is the mathematical equation behind it. So I'll try to give you a demonstration of all the mathematical equation, but yeah, so don't try to mug up all those mathematical equation. It's going to be a little bit complex. But you all will be able to understand technically that why we are going to use an optimizer and what is the purpose that it is going to fulfill during a neural network training. Let me share my screen so that I can write it down something over here. So here, a neural network optimizer. Yeah. Now, the very first question which arises over here, that what is optimizer, by the way, and where we are going to use it. So if you remember when I was talking about a neural network backward propagation, so I have written something like weight new is going to be a weight old minus eta, which is a learning rate, and then partial order derivative of a loss with respect to the weight, the old weight obviously, right? Now this is called as optimizer equation. This is technically called as optimizer equation. Now there is a name to this particular equation that we are talking about. So optimizer is an algorithm, or technically it's a mathematical function which minimizes a loss, right? Which help me out in terms of minimizing a loss by adjusting a weights and a biases of a neural network during a training. And we have seen that yes, this particular equation, whether it's a weight equation or whether it's a biases equation, so where new bias is going to be old bias minus eta, partial order derivative of a loss with respect to a bias, old bias. So this was helping me out in terms of finding out a new weight and a new biases, and eventually, right, when I'm able to find out a new weight and a new biases, so I'm able to decrease a loss. Simple, right? I was able to decrease a loss. So this entire optimizer is going to help me out in terms of decreasing a loss with respect to whatever learnable parameter that we are going to consider. Now, so in a generic manner, I can write this equation maybe in this way. So theta is equals to a theta minus eta, which is a learning rate, right? And then a delta. So then a delta of L with respect to a theta. So again, this equation is not different and not complex. I have just rewritten this one in a generic way, right? That anything new is going to be anything old minus eta, and then partial order derivative of a loss with respect to that, and technically this is what I have written even over here, and technically this is what I have used even before. So when I was trying to talk about a backward propagation, and where I have done a very lengthy calculation, a mathematical calculation to adjust my weight starting from weight 1, 2, 3, 4, 5 and 6, and then my biases B1 and B2. So this is actually called as optimizer. Now there is a name to this optimizer, by the way. So there is a name called as stochastic gradient descent. Let me write it down. The very first optimizer equation that we have already used, but we were not aware about it, right? So it's called as SGD. The full form is stochastic, STOCHASTIC gradient descent, CENT. So there is a name to this equation in a generic way. Theta is equals to old theta minus eta, partial or derivative of a loss with respect to the theta. In a generic way we can write it down this one. But yeah, it's nothing different. Don't get afraid about it that we are trying to learn something new. We are not trying to learn something new. It's the exact same thing that we have already learned. Now we are just like trying to find out that, okay, this is what it called. So it's called as stochastic gradient descent. And what is the what is the benefit of using a stochastic gradient descent, or what is the special thing about a stochastic gradient descent, SGD? So basically it try to update your weights with a single sample or maybe a a small batch of the data, means maybe 2 or 3 records. Based on that, it will try to update your weight. So this is the reason. So we have passed one iteration, so one row x1 and x2 we have passed, and then in a backward propagation, so we were trying to update it. So this is called as stochastic gradient descent. So where it will try to update my weight or any parameter, maybe a weight and the biases, based on the single sample or maybe 2 or 3 sample, which is called as mini batch, right? Mini batch. So it's very simple equation. It's a very fast equation. And again, it works very well with respect to a large data set. So you can feel free to use a stochastic gradient descent, right? You can feel free to use a stochastic gradient descent, but there is some drawback. There is some drawback of this stochastic gradient descent. So generally it gets stuck with respect to a local minima. Local minima means what? So we are trying to achieve a local minima where loss is equal to 0. So we had some loss, then we are decreasing, then we are decreasing, then we are decreasing, and we are trying to fall here. Now let's suppose we are trying to pass a small batch of the data, or maybe after one data itself we are trying to pass, and we will be having so many losses, we'll be having a global minima, global maxima over here. So we have to achieve a global minima, means a loss which is minimized with respect to the whole data, right? Whole data. But what this stochastic gradient descent says that, okay, I will be able to apply this equation, means I will try to change a weight and the biases, whatever learning parameter that you have, even with one data or even with a couple of data, not whole data, right? Even with a single data or maybe even with the mini batch of the data. And that is going to cause for this one to stuck on a local minima. Local minima means like just trying to maintain a loss, just trying to decrease a loss based on couple of input, couple of data input, right? And that is a problem. That is a big problem that you will be able to find out with respect to a stochastic gradient descent. The second problem is that it never adapts a learning rate, the constant that we are going to use, the eta that we are going to use. Now, so there is a new optimizer people have introduced, scientists have introduced, saying that okay, let's try to use this one, and here, so I'll try to maybe mitigate the issue that you have been facing, right? You have been facing. So at the end of the day, I have to update, I have to find out a new value of some parameter, maybe a weight, right? With respect to old value minus this whole term over here, which is helping me out to change the value. I can write it down maybe as a VT, right? Maybe as a VT, I can try to write it down. Now, what is this VT? So they say that okay, so this parameter, this one that you are trying to use, so maybe we can try to make it momentum based, right? So maybe it is going to take a accumulated gradient and then it will try to change it, just the way we try to see a momentum in a physics, right? We can try to see a momentum in a physics. So on the same principle, they said that okay, I can try to derive one momentum based optimizer. So what is this momentum based optimizer? What is the formula for this momentum based optimizer? So obviously theta is going to be, new theta is going to be old theta minus VT. And this VT is what? What is this component? So this VT is nothing but a gamma V t minus 1, means the previous one, plus eta into a partial order derivative of a loss function, right? So they have technically introduced this particular term. They said that next one, momentum is what? So obviously momentum depends upon the previous instances. So in the similar manner, they said that okay, so whatever changes that you are trying to make, now just replace this entire things with this entire equation. So you will be able to see that this is the new component which has been added. Yeah, this is the new component which has been added, and this component talk about basically a past one, right? They said that okay, so I'm going to try to use a momentum over here, so which is going to help me out to even adopt something from the past, because in a case of stochastic gradient descent, there was no past. It was trying to do some sort of a changes based on the current calculation, based on the current data which is available to me. So this momentum is something that they have introduced. And then based on this one, again, there are a new equation which people have kept on introducing. But at the end of the day, the philosophy was simple: how to change a weight and the biases, or how to change a learnable parameter, because that is very much important for any kind of a neural network. So keeping that in mind, the third equation that we are going to talk about is called as NAG. It's called as Nesterov, Nesterov, Nesterov accelerated gradient. Accelerated. Now objective is same, right? Objective is same. Again, this is my objective at the end of the day. I'll keep on playing with the VT, by the way, right? I'll keep on changing the value of the VT. So objective was same. So new theta is going to be old theta. Old theta means old value, and then a VT. And then I'll try to play with the VT. Maybe I can try to change the equation of the VT. So here in case of Nesterov, so they have given a new equation, this particular part, this particular component. They said that okay, so this gamma Vt minus 1, which was same as a momentum before, plus eta partial order derivative of this one, but not just with respect to the theta, means not just with respect to W or B, but with respect to theta minus even gamma V of t minus 1. So this time I'll try to find out the partial order derivative, not just with the weight or the biases, but with respect to the the previous value as well. Plus here we have a component. This was the changes which was made, right? This was the changes which was made. And here, so what it does is, so it will always try to look ahead before computing the gradient, which leads to more accurate update. So this is where this Nesterov comes into a picture. Then people came up with another equation. So again, people are playing with the VT. At the end of the day, everyone is playing with the VT, right? So there is something called as Adagrad, 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 basically. So it's called as adaptive gradient algorithm. Adaptive gradient algorithm. So where again theta is equal to, new theta is equal to theta minus, I can say, minus VT. Now what is this VT here now, right? Which is the value responsible for changing things. So here it's nothing but eta divided by root of capital GT plus epsilon into partial order derivative of loss with respect to theta, means with respect to the input value. So here, what is this GT and what is this like the epsilon that has been introduced? Because eta we know it's a learning rate, and this we already know. So it's a partial derivative of loss with respect to the input, with respect to weight and biases. So what is this GT, by the way? So GT over here is nothing but sum of the square of the gradient. So basically GT represents sum of a square of the gradient up to timestamp t, till t, right? So till we are trying to find out the value. And epsilon is nothing but it's a constant, so a small value basically to avoid a division by 0. So if this is going to be 0, let's suppose for the first time, so if we have a 0 value, so in that case we don't want divided by 0. So that's the reason. So people have introduced basically epsilon over here. So it's nothing but a small value to avoid division by 0. Yeah. So this is called as Adagrad, by the way. Now, so there is another optimizer which again scientists have introduced, and that is called as RMSprop. Yeah. So it's called as root mean squared propagation. So again, objective was same. New value is equals to old value minus some VT, right? So now here, if you are going to like find out the value of VT, right? So here the VT is nothing but here it is going to be eta divided by root of E of, I can say, g square at time t plus epsilon into gt. So this is going to be the value. So this is going to be the value of a Vt. Now here, so we are able to find out a lot of new terms. So E of G of square T and GT. So this is the new value that we are able to find out. Now what is the value? What is the meaning of this E of G of square? So the value says that E of G of square at time T is equal to beta. So beta is basically a decay rate. For example, like a 0.9, 0.8, we can try to consider E of G of square at t minus 1 plus 1 minus beta, again decay rate, into gt square. So this is the value of this particular component, right? So this is called as RMSprop. Now moving ahead, so there is another activation function that you will be able to find out called as Adam optimizer, one of the best one that you all will be able to find out. So I think it's a fifth one. Yeah, it's a sixth one. So there is a optimizer called as Adam optimizer, one of the widely used optimizer, which is called as adaptive moment estimation. Adaptive moment estimation. Now how does this looks like? So here again, theta philosophy is same. Old theta, old value is equal to, new value is equal to old value minus, and here they have introduced eta divided by root of v of t delta plus epsilon into m of t delta, right? So delta. Now what is this vt and mt, which is the new term which has been introduced over here? So let's try to talk about that. So here your mt is nothing but beta 1, which is again like a decay, or we can say a momentum. So beta 1 m of t minus 1 plus 1 minus beta 1 g of t, and vt is basically beta 2 vt minus 1 plus 1 minus beta 2 gt square. So this is the meaning of vt and like mt that you all will be able to find out. So what is the value of m hat t? Because we are using m hat t and vt over here. So m hat t is nothing but mt divided by minus, not plus. So 1 minus beta 1 t, and vt hat is nothing but vt divided by 1 minus beta 2 t. So mt and vt, where beta 1, if I'll talk about, so beta 1 is nothing but, let's suppose, a 0.9, which represents a momentum. Or what is this beta 2? So beta 2 is nothing but 0.999, which represents basically adaptive scaling. So this is one of the best optimizer, which is a combination of momentum and the RMSprop that we have discussed. So it's this Adam optimizer is adaptive momentum estimation, right? So it's a combination of basically a momentum optimizer that we have already discussed and a RMSprop. And again, most of the places you are going to use a Adam optimizer. It's one of the lethal optimizer that you will be able to find out. So where it combines two things, momentum plus RMSprop capabilities. But at the end of the day, when someone is going to ask you that, try to explain me an optimizer. So if you have to explain the optimizer part to anyone, right, to anyone in this entire world, you will simply say that a kind of an equation, a kind of an algorithm, so which is helping me out to find out a new value of a trainable parameter, and eventually new value of trainable parameter. Why we are trying to find? So that we can decrease a loss. So optimizer is an algorithm which is helping me out in terms of decreasing a loss by finding a new value of a trainable parameter in a backward propagation. That's the whole idea. That's the whole meaning of an optimizer. And we are going to use an optimizer throughout our neural network, throughout our deep learning or computer vision or NLP or generative AI journey. So when we are going to write something, when we are going to write a code, obviously we will be talking about all of these things again and again and again, almost every time. We'll be talking about that when we'll write the code. So hope this idea is pretty much clear. No need to mug up anything. So we are going to use all of these things so many times during the entire lecture that you will be able to remember for the lifetime, right? Lifetime. As of now, try to understand the intention, that why we are going to use it, what we are going to use it. Then it will help you out to understand things in a much better way. With that, thank you so much everyone. Take care and see you again in my next lecture.